Hello, everybody, and welcome to yet another episode of Undercooled. We are again on site in Atlanta, Georgia, just finishing up the NAMES conference at Georgia Tech, and we have another special guest with us for this episode. We have the one and only Alison Polasik, who I won't introduce because we'd like her to introduce herself. So, Alison, welcome to the show, of course. And could you just tell us a little bit about yourself, where you came from, what you're doing now?
Yeah.
And, of course, why you got into material science.
Right. Very important. So, yes, I am an engineering professor at... Sorry, I need a second. Sorry. I'm an associate engineering professor at Campbell University in North Carolina. And I teach there a whole bunch of different classes, but of course the most fun one is material science. I got into material science kind of a circuitous way, but I just started doing, once I realized I couldn't be like a musical theater star because I can't sing, I started looking at engineering and just went to like high school outreach things held by women in engineering at Arizona State and got to look at a whole bunch of different engineerings, and material science was just the most fun. Like there was a lot of interesting parts about it. I liked the physics, the mechanics, there was biomedical aspects, but it was all just solids of chemistry. So that was just the most interesting to me, and I've never turned back. All 3 degrees, material science.
So you just went and decided and said, I'm going to do this, and you took the classes, and that was it.
Yeah, I mean, I was one of those rare ones who went in like first semester, I'm in material science and engineering, and then never wavered. So
we found our unicorn.
Yeah.
So let's just go straight off script here.
Okay.
What do we do to find more students like you? The students who actually, as soon as they get that first taste of material science, they're just hooked. Because a lot of students come to us saying, oh, I thought I was going to do X, or, oh, I never, but it seemed like you were just on the path. So where are the others?
I think, so I was unique in that I found out there was a path, right? Like a lot of students, if their high school teacher doesn't know about it, or they don't go to a program like I did that kind of showed all of the engineering options that were out there, then they don't know that material science and engineering is a thing. So that's one way, I guess. I think the other thing is, I think our students are smart and they want to have a lot of good job prospects, and we don't always do well, I don't know that it's our fault so much as a community of material science, but there's not a recognition that you can do all of those things with a material science degree and how just useful it is. When I was at Ohio State, I taught like a 1-credit class with a colleague of mine, Tanya Nocera, who is in biomedical engineering. And it was just about, okay, if you don't want like to go for grad school, like how do you market yourself as a student with an engineering degree that maybe HR managers haven't heard of? So I don't know that there's one answer, but the people who would be like me maybe don't know that material science is an option. And some universities it's not, but yeah, I don't know.
Yeah, I remember going back to my high school for some reunion. I won't say what number it was. It was large. But I was really upset because I got into one of the science classrooms. They were showing us around the high school that, we went to, and they had an engineering club. And I thought that was great. And they listed all the engineering disciplines, and material science wasn't there. And I hit the roof. First of all, I went up immediately and defaced their poster and I put it on there. But my real fear is that the person who runs the club doesn't even know what material science is.
Yeah.
And, it was on a weekend, so I couldn't really talk to anybody. But that's probably more the norm than the exception. And I think it's a huge problem. How do we get high school principals to understand that this is a field that they need to check? I don't know if it's principals or superintendents or the person who's in charge of science curriculum for a district, because it's not just high schools. It's also the middle schools and even K through 12, we need this on the list.
So I would change the question to how do we make sure that it's benefiting their students? Like, it helps us if they share that material science and engineering is an option. But I think what everybody wants for high school is, and so maybe it needs to come from a different place, like the companies or people that want our students, making it clear that that's a great opportunity. And I think one of the strengths of material science actually is the way that our field really bridges a lot of, a lot of different careers, not just at the BS and engineering level. Like there's welding, there's machinists, there's manufacturing, all of it use material science because everything's made of stuff. And so that level of, it's not just about getting a bachelor's of science and engineering, because that already limits the pool of 18, 17, 19-year-olds thinking about their career. So maybe that's an avenue we can think about.
A quick thought before we go further in that direction.
Yeah.
A recruiting object, artifact, whatever, that might be really useful would be testimonials from people who are doing hiring. I'm thinking technical managers in the big companies like Dow or like Boeing or, any of these really large clout name brand institutions. Right. Why not have their managers putting down in writing, here's why I want people who know about materials. And then we show that to principals, to guidance counselors, to college counselors for that matter, so that they realize that it's not just us trying to sell ourselves, it's being pulled from outside and saying we need more students with this skill set.
And that's an area where I'm still pretty ignorant of, as far as how does we know that the people we talk to, the technical managers, are like, yeah, material science has amazing skills that is valuable in a variety of careers, but do the people who our students' resumes are going to know that? Do the people at the hiring fairs know that? I mean, where are some leverage points where we can make an impact and help that communication?
Yeah, you're absolutely right. And it really should be focused on future jobs, because it's not just the students that we need to educate, it's their parents as well. Yeah. And their parents want nothing more. I mean, we just had a whole talk with Ron yesterday about exactly this. Parents want to know that their kids aren't going to end up living in their basement. Parents want to know that they're going to be able to go and get an amazing job, have a wonderful career, and take care of them when they're 90. So, yeah, it absolutely needs to be focused on the student and what their career opportunities are going to look like. But as always, the devil's in the details. Yeah, we need to get managers hiring people to write testimonials, but how do you actually do that? That's really difficult to do. We might be able to do it through our societies, because there are a lot of industrial folks in the societies, and but it almost has to be an effort at the TMS, the MRS, the ASN level. Ceramic Society. I mean, it's incredible how every industry uses material science. Mm-hmm. It's the only recession-proof discipline of engineering, because if energy goes down and transportation goes down, there's still electronics or making things out of steel for other purposes. And while it won't protect in a depression where everything goes down, it will give a lot of flexibility to students throughout their career, unlike a lot of mechanical engineers and a lot of chemical engineers who are much more pigeonholed with their careers once they start working. But it's really hard to have that conversation with parents or high school kids.
Yeah, and I mean, I would probably come at it from a slightly different angle than starting at the TMS and the ASM, but like really, and that's maybe like I'm just always driven kind of like by curiosity, like what are the students thinking? Like what is motivating the students who are going out? And I think engineering in itself is so opens so many doors. Like we teach our students to solve problems, to break them into smaller pieces, and the specific like crazy sexy cool of material science that just grabs us is going to grab other students as well. And it's that combination that makes engineering in general, but material science in particular, just because you can do so much with it. So much. There's so like I could transition to be a polymer person. It might take a while, but like to figure out all those things. But yeah, like so.
So going back to something that you mentioned a couple minutes ago, there are all these other career paths like welding and machining that are very materials adjacent. So I was hoping you could talk more about what you're doing at Campbell, because it's not you're not preparing students who are going to be material science PhDs. They're going into other career paths for the most part. So what does that look like, teaching material science to students who have other career intentions?
Yeah, I would actually say so. At Campbell University, it's very different. We both went to Arizona State. I went to Ohio State, University of Michigan, all these big, very, very big schools. And the program at Campbell is a Bachelor's of Science in Engineering. So we have focuses, but it's a degree in engineering. And so our students are actually taking many, many of their classes together. All of our electrical engineering students take fluids, which is really interesting because then there's so many corollaries between the flow of electricity, flow of electrons, and the flow of other like molecules of fluid that it makes for some interesting conversations in that class. So all that to lay the groundwork to say when I'm coming in, I'm teaching not just a materials science class, it's a materials and processing class. So we come at it from a processing standpoint. And we do a lot of hands-on. And we can, because we're a smaller program. My classes are capped out at 24 students. So, and my classroom is like maybe 20 by 20 feet. I don't know. I haven't measured it, but like a normal size classroom. I could, if it weren't full of other things, I could probably fit 50, 60 students in there. But I've got tables and chairs for 24 in one corner. And the rest of the classroom is all of a material science laboratory.
Oh, okay.
So it's not even like, I don't even have to go down the hall to get a question answered. It's like, oh, well, what does this look like? Well, I don't know. Give me a few minutes to go set up the tensile test and we can do it. We've got like the microscopy and the corrosion center and the lab, the fume hood and everything set up there. So that allows us to come at it from a very, I want to say purposeful, but I don't know if that's the right word, but applicable. Like it's very applied material science. We're learning corrosion because this is what it looks like. We're learning about phase transformations because it's going to be important if you're using this steel or this steel. And a lot of our students are working in our machine lab. So they're like, oh, so that's why when I work with aluminum, it feels like this. And when I'm working with mild steel, it's like this. And why I can't cut such and such. I can't cut tool steel with such and such tool kind of thing.
Let's back up just a little bit.
Yeah.
So fascinating classroom. I wonder if you could send us a picture. We could.
I definitely can. Yeah, for sure.
Put it into the video while we're talking about it. While you're talking about it, but so there's not a material science degree. It's just
Correct.
one engineering degree. So I'm curious what your curriculum looks like. How many materials courses do the students get?
Right.
How is that blended into capstone design? Because, I think most of us at these big universities where we have our own materials programs,
right,
we all have like the same curriculum, but yours is going to be really different. So
yeah.
can you talk about the student's path to learning materials in the context of the degree at Campbell?
Yeah, so I think that path is informal in a lot of places because there's so much, like they are actually they're building a robot, they're building a fish tank their first year. They've got a very in-depth design project in their first year where they're building a prototype. So they're evaluating, like, should we use carbon fiber or PVC? And like, should we use, trying to think. So they had one where they were doing kind of a grip assister for somebody with, and I'm sorry, I forget the physical disability, but so where their hands were really clenched, and so that it would allow them to manually pull their hands back and kind of grip it. And so like fishing line, and like what was the thickness and how much tension can you get from things. And so they're getting that very implied early on. And then second year, usually they're taking my class and we're thinking about, okay, why? What's the structure that gives us that? And how can we put a property and name to that thing you want it to do? And then mechanical engineers get a whole class in mechanics of materials and manufacturing. Certainly materials properties comes back up in heat transfer. I'm trying to think. I mean, I bring it into thermodynamics when I teach that. I definitely have it in statistics when I teach it in statistics, but that's, instructor's choice. And then in the final projects, my course.
The course that you teach that's on materials.
Yeah. Okay.
What does that look like?
So materials, science and processes, we use the Callister book. It's a integrated lab course. And so while there is like all of the curriculum and some reading and worksheets that we do in class, there's also labs, some classic labs and a lot of little activities. So when we start talking about defects, I'm like, okay, let's just go to the cabinet, and we get out like cookie sheets and BBs, or like the bubble raft experiment. And that, it just doesn't take as much time. It's not, there's the activation energy for doing all this hands-on stuff is just so much lower because of the built environment. We also have a final project where they have to go find something. And I do say metal because we have a metal processing, like it has to be metal, but you have to go and look at it and do research, but then prove like this is how it was processed. This is what it's made of. We have an SEM with EDS. So that helps with that. And that's like their final project and a poster that they're doing for this class. So it's, yeah. And it's all like a lot of team-based, like there's individual homework, but everybody's in teams in the class working on things. So there's that component as well.
So on these final projects, what's the like craziest or, most surprising, the one that sticks out in your memory of, oh, I remember when students did this one?
So they had one where they were looking at pennies from across the century. So somebody had like a 1930s penny. And I think what was interesting was they ended up, when they were doing their research, how much it changed from year to year was interesting, because sadly, I think that one, there wasn't a huge difference between the pennies that wasn't explainable by diffusion. But that was just because of the years they had. And then... Did
you get any zinc ones from World War II? Because they switched to zinc.
Right, yeah. No, so that's what they did the research. And I was like, oh, okay. And it was more of like a leading, like, well, why might they change out of copper? And why? So they found a lot by doing that research. And it was a really good conversation about, the use of materials is driven by other things than just, availability and economics, and kind of getting into kind of criticality of materials. And that was a nice segue into that. Yeah.
One thing you might consider, one of our alums, it was a long time ago, he worked for the company that the European Union had them do consulting with, because they had a problem with the EU with the euro. Okay. The euro is a bimetallic coin.
Right.
And they wanted it like the loonie in Canada.
Okay.
But the Canadians did it right. The Europeans screwed up. And they noticed when people had a euro in their sweating hands, mm-hmm. their skin was being coated with aluminum. They didn't match the materials right, and they were getting electrochemical cell when someone held it.
Oh my God.
And they had to go back and redo the whole thing.
What does the Looney use? Like 10 or?
I don't really
Yeah.
know, but
Okay.
that would be a fun
That-
thing for
okay,
your
that I can do.
students.
I think I've got a Looney left over from ASEE.
Yeah, that's
So.
good because it's probably hard to get these days. It's 25% tariff or something.
Yeah, and $1.25. Yeah.
So you said smaller classes,
Mhm.
max 24, give or take. With having a smaller class like this, what do you find are the differences in teaching a small class compared to large classes? And not just the scale of workload or things like that, but the ways you can interact with students or the
Mhm.
opportunities that come up to be spontaneous. How does that environment change when you have a small?
It is not very scripted at all. Like I go in with a very loose idea of what we're talking about that day to a certain extent. I mean, I have like, this is the topic. I do worksheets because it kind of keeps me from going off on a tangent too much. I can have a tendency to do that. And so the students will keep me on. There's always at least one student's like, are we going to talk about this? It's on the worksheet for today. And I'm like, oh, right. Yes, let's do that. But yeah, I mean, and it's kind of like, it's my lab. So I kind of have that real golden opportunity of like high school teachers get, where like, this is my classroom. So I've got like 2 magic drawers of demos. And it's like, so we're talking about metals and they're like, well, what about polymers? I was like, well, let's break out the chain, like the beads and the chains, and talk about like, what does deformation look like in polymers? Because, we start with a nice metallic crystal. It's understandable, but they have the question. I'm like, well, we don't have to wait till chapter 15 to talk about that. Like, just break out my toys.
That connects really nicely to something that I know was a discussion topic at NAMES, which is that learning really should be non-linear. The textbook takes you from the beginning to the end in this beautifully crafted sequence, but that's not how most of us discover all the things that we know about all the things that we know, not even just material science. And so it's really great that you have this opportunity to say, yeah, let's learn it now instead of later. Why not? If you want it now, let's learn it now.
Yeah. I mean, it's a great opportunity, and it's a gift of the position that I have and the way that I'm able to teach there. But I think, so when being at Campbell, I also don't get to stay in my wheelhouse all the time. So I taught fluids one semester, and that was interesting. But what did I do as an instructor? Because I followed the textbook. And so the textbooks are there because they're like, I think of it like like the walker. Like, it's like, okay, it's giving me some support as I'm learning something new. This is, if not certainly not the only, maybe not even the best for me, but it does have some logical flow to it.
I was thinking of bowling bumpers.
Yeah, like I'm not going to go too far off the rails. Like the ball will still get down to the end. That's probably a better analogy. So yeah, I mean, it's good. Textbooks are good, but they are powerful in the hands of an expert who can flip through and be like, okay, well, this is the 2 pages that you need to read right now, and then come back and chat, and we can have a whole discussion about it.
So I wonder, using a textbook like as a random access expert, it's kind of what Wikipedia is. It's kind of what ChatGPT is. And I wonder if using it like that is going to obliterate textbooks.
Yeah, I mean, so I think it'll be an ebb less than an obliteration. If anything's going to obliterate textbooks, it's the fact that the students don't know how to use them. But like, I've got my textbook on my desk. And so when I need to show a grain structure, I'm like, oh, wait, hold on. Let me get you this really good image from this textbook. And then I'm just putting it on the, like a document camera. So that's still always going to be my first go-to. So as long as I'm around, textbooks will still be in the classroom.
So there was a talk at NAMES just yesterday.
Yeah.
Where the computational scientist said he never understood brain growth at the atomic level until he did a simulation. And I'm like, what? I said, just look at the picture that's in Callister. And I went over and showed him because I had it in my lectures. And of course, that goes back to Cyril Stanley Smith and Bull Mullins, all the curvature-driven phenomena that was all explained before there was ever computational material science, but something that's either in compression or in tension, right? If it's in tension, it's easy to pull an atom out and let it migrate, one angstrom over to become part of the adjacent grain. And that's the whole basis for curvature-driven phenomena. And it is energy. But the picture is so important. And that picture is right in the textbook. And we all know where those pictures are. So that's it. It was interesting.
What's interesting to me about you saying that was because I liked, so at that, I forget what the term he used, what Jake used, for that, having a new way of like visually accessing the information.
So restructuring or restructuration?
Restructuration. So when I learned grain growth, I was at the University of Leeds and we were blowing bubbles. And so it was that idea of like, okay, you've got two bubbles and it's the volume, the energy of the volume versus the energy of the surface.
Yes.
And so that was the piece that my brain kind of grabbed onto, and then it could add the other things to it. You kind of came at it from a different place. But we can all agree that what he showed yesterday was the equation for it was not the one that was going to make us understand it. Like seeing the equation, or at least for most students, seeing the equation isn't like, I think of it like a grappling hook. Like you want to get close to this whole idea. Okay, well, you need something for your brain to stick into, like get those neurons to fire together. And then you're like, oh, now that I'm here, I can kind of see it from all these different angles and really start to get a sense for it and see the beauty of it and where and all the places it plays into. So
one thing I was thinking about during that talk yesterday is superconductivity. So stick with me here. We're going somewhere.
Yeah.
But I remember in my graduate solid state physics course, we were learning about superconductivity and Cooper pairs and things like this. And I remember the instructor, doing all these beautiful Fourier transforms and putting things in frequency space and showing, oh, yes. And then we have, this zero in the complex plane that we can integrate around. And I'm like, okay, cool. You can calculate it. But what are the electrons doing? And he just looked at me like, well, it's right there. And I said, no, it's not.
Yeah.
What you showed me is that 1 over omega minus omega prime is whatever, but where are the electrons in physical space? And he was just like, it doesn't even matter. So that was a moment, but, seeing the physical display of where are the atoms, what are they doing, how are they interacting, and coupling that to the equations so that students can see, oh, this animation, this static image, this equation, this verbal description, if there's something tactile like blowing bubbles, all of those interlinking with each other is where fluency and expertise comes from.
Absolutely.
And that's something that I feel like is teachers, especially in the K-12 space who have more training in pedagogy, just know that. They've been taught it, right? And there are still, I feel, too many of our colleagues who don't realize that that is such a critical element of achieving mastery and not just competency in the subjects that we teach.
Yeah.
So just to follow up, Tim, you're basically saying we should be mechanistic when we teach because physical mechanisms are what allow people to understand things, not just equations. And although I will say, the concept of delocalization makes it much harder to think physically, but you can talk about delocalization by pointing out actual experiments and observables that cannot be explained without the concept of delocalization, like diffraction. But even in diffraction, you can statistically get to the mechanism. Every single electron that goes through that double slit does go somewhere. But in some, it looks like it had been delocalized as a wave. And that's a physical mechanism, right? And Cooper pairs are the same if Cooper pairs are even the right model, because we're still not exactly sure about superconductivity, which is why it's such a cool field. But I really dislike anything where they don't talk about the physical mechanism, whether it's soap bubbles with volume and surface energy and balancing that. That's a beautiful mechanism. That's something you can understand. Or thinking about the atoms on the surface of those things and the state of stress that they're under, or how tightly they're bound. Both of those work because they're a physical mechanism.
And I think even more than that, like as you gain experiences instructor and you think about the different ways to explain it, one of them is going to work more for one student than for another. And so being able to, again, that kind of adapting, or at least having multiple ways of explaining something, especially something very complex, is really important, because our students come with their own brains, with their own connections, and certain tools are going to work better for their understanding than others.
That leads right into my next question. So you mentioned that you also teach thermo, and I presume you teach it to all the students, not just to...
Well, there's 2 thermo classes. I teach both. I teach the one that everybody takes. And I also I teach that one occasionally. And I teach every spring, I teach the one that the mechanical engineers only take, which is like internal combustion engines and Rankine cycles. And so.
But you probably don't teach the thermo course that we teach in material science programs. And so how do you, I'm sure you can't help yourself but get some of that into the course. So how do you do that? And then when we're done this, I need to have a discussion with you about heat pumps, because I'm thinking of getting one and I don't really understand how they work. But since you teach that mechanical engineering version, you're an expert.
Well, I don't know an expert on how, like, to choose between the anyway, yeah, we can chat. How it works, yes. Okay, so where do I bring... So one of the things that I don't get as in trouble for using this phrase at Campbell that I did at Ohio State a little bit was, well, that's God and thermodynamics. They decided that. So I bring thermodynamics in a lot of little ways into my materials class. So I bring the general idea of thermodynamics, like where energy is always conserved. Like, why are things heating up when they're deforming? With bonding, like the fact that bonding relates directly to 3 materials properties, but that we really can't change bonding without changing the chemistry. Like, God in thermodynamics said, this is what an aluminum-aluminum bond is. And we can change the relative proportion of them, but we're not going to change that. And then I like to show examples of how, like a phase diagram, explain like, okay, well, this phase diagram was somebody's entire PhD thesis in 6 years of their lives. And now we can simulate it because we understand enough about the thermodynamics, and how that's maybe a bigger question about how fundamental science and fundamental knowledge helps improve our understanding in so many other ways. But then when I teach thermodynamics and we get into entropy, like diffusion and just mixing are such a great example of entropy that is very accessible. And so I kind of more bring the materials aspects of thermodynamics into my general thermodynamics class, and the more general thermodynamics into my materials class, more so than try to bring the materials thermodynamics into my materials class, if that makes sense.
There's something there about entropy of mixing, but I'm not clever enough to come up with it right now. But
okay, you know what? You can add the joke in post-processing.
Okay, great. So another topic of conversation in the conference has been how tactile material science can be, because we're surrounded by these concrete columns and these weird woven whatever polymer they are chairs and all that. And it's all around you, and you can't help but be immersed in materials every moment of your life if you open your eyes and just touch everything around you. And in a smaller class, I have to imagine that there are opportunities to do more hands-on stuff, because I guess I'm trying to ask more about this sort of hybrid classroom setup where you're in the lab and it has a lab component, but you're also lecturing, and like there are so many institutions where this is the lecture class, this is the lab class. And I feel like there are a lot of lost opportunities for students to engage with the physicality of the material when you have those 2 components isolated from each other.
Yeah, and I do think that while I'm very fortunate to have the physical setup, there's a lot of great educators, and we were chatting with them at lunch all this week, and we know a lot of these people that are doing a lot of the same things just by having smaller classes or having enough IAs to help get a reasonable ratio between instructor and learner. And there's so much you can do by bringing stuff into a traditional classroom as long as it's not a lecture hall sloped. What I am able to do a little bit more easily, and I've kind of had to learn how to do this, is break the class up into pieces. So like when we're doing a lab. So maybe you guys are polishing, and then I'll come over here and talk to people about the theory behind etching and like what's going on with the corrosion and why are we going to see this and why would we choose this etchant versus this one. And then over here, they're, maybe researching their project and like, okay, well, where are you going to be looking for information, and show them, oh my God, the ASM handbooks have everything you could possibly want. And they're not actually that hard to look through. So there's the ability to craft what I'm teaching at almost every level to what the student needs. And I don't always do it perfectly, for sure, but I have that ability and that freedom, and it makes it a lot of fun.
Do you do things with, I think they call it jigsaw learning in this,
Oh, yeah.
where so you'll farm out different parts of a problem to different parts of the class, and they have to all put it together?
I love it. Yeah, it's one of my favorite tools because it's very much like you go learn and then you're going to teach her. So we could talk for a long time about jigsawing. They're great.
So you've been at Campbell now for what,
7
years?
years.
7 years.
Mm-hmm.
So again, because it's a relatively small number of
Mm-hmm.
students that you touch, you probably have a better handle of what they've done since they graduated than we do at larger institutions. So, while measuring learning is an incredibly hard thing to do and very complicated, ultimately, it's how the students do that really matters.
Yeah.
So do you have any thoughts on how your students do? I mean, you have an interesting window in that you can see a large percentage of the class, how they ended up, and feed that back into your thinking about education.
So, so I'll take that in 2 steps. So seeing how they end up. I'm really impressed with the students that I've had at Campbell with, again, and, so this was our 5th graduating class. So I've been there for 7 years, but we've only had 5 graduating classes. So in that time, like some of our students have like moved from, and I'm not saying like this doesn't happen at other universities, but really moved from companies and different types of jobs. And I think that speaks a little bit, not certainly to the the job market. They could go for a lot of things. They could easily stay in their wheelhouse and kind of progress in this area. But that fact that they feel comfortable moving from state jobs to private companies, like doing water testing and system design, or like going to work for electrical car companies, or a lot of different jobs within the pharmaceutical industry. So even when they're staying at, say, a Novo Nordisk or a Pfizer, they're moving from production to quality assurance to other, trying to think the most recent jump that I saw on LinkedIn. So it's really interesting to see that they have that kind of multiplicity of options, and they recognize it, and they're taking those opportunities, because that's what I would want. I don't want like necessarily just one career my whole life. Like I want like 6 or 7. Like it's all so interesting. So that was, and I forgot what was the other part. You said 2 parts.
And that was it. Just
okay.
Yeah, and just measures of student success in terms of their overall life trajectories and how that affects what we do as educators, right? That we go out, we see the ways in which they succeed, and then hopefully bring that back to class and say,
thank you.
How do I do this?
That brings that back. So because we're small, I can also talk to them. a lot. They come back to visit. And we are always asking it, so what was really helpful? What would you, and so we had in the spring, one of my students, Madison, was there for something else. I was like, would you like to talk to the class? And she's like, I don't want to interrupt. I was like, come on. They want to know what it's really like to be an engineer and what you've learned in the first year way more than they want to know about the lever rule.
Right.
I'll cover the lever rule with a video later. Like, please take over this. And of course, that's what the students would not get, that's what they want. So we get a lot of feedback about, what was really helpful, what was not. But yeah, and being able to have a shorter cycle of improvement. I think it's really easy a lot of times to, especially when you have 80 alumni in a year, and then you only hear back from 6 of them.
Right.
It's really hard to know if their feedback is indicative. And it's hard to make decisions based on that. So that's one of the strengths, too, of a small program, that we get enough feedback from a significant proportion that we know that it's worth acting on.
Yeah, that's an area that, to be honest, I think we've struggled with at Michigan, is really staying connected with our students after they graduate, not just immediately of, oh, yes, you placed into this job, but 5-10 years down the road, how have their career paths changed, and getting them to come back and to talk to our students. We do some of that, but I would love to see more of it, because just exactly as you're saying, our students would like nothing more than to hear from someone who was in their seat 5 years ago and what has helped them in the time since.
Well, I think I don't know any big universities the size of the University of Michigan's that are getting great responses on their alumni surveys. I haven't seen it yet, but if anybody's going to do it, it's going to be material science program, because we tend to be smaller. Like, the thing I heard always is, like, from students is a PEV, and you probably did too. This one feels like family. The mechanical engineering students, they're always like one of 2,000, but we cap out at like 100 students in undergraduate at even the biggest programs. So we have more capability than other majors do, but it's still hard. I don't think it's anything on Michigan's that they
Right. And we do get a lot of students who come back to recruit for their companies.
Yeah.
And frankly, I wish more faculty would come to these presentations to the students, because they would get much better feedback of how they did. But they don't, they're all busy. But, interviews, focus group studies are often far more valuable than surveys because of the low response. I mean, nobody likes surveys. I hate surveys. I don't fill them out. I can't. Surveys almost always hurt me.
Yeah.
Because they use the data to do something that I probably don't want them to do anyway.
There's that.
And it takes a lot of time to fill them out. And so having people come back and talking to them or meeting them other places, I just think that's invaluable, actually getting to talk to them.
Yeah.
So one other big activity, so there's 2 activities that we haven't talked about that I know you're very involved in. One is you are an engineering education researcher.
Yeah.
And so I'd like to hear a little bit about how you do that at this small school. What are you working on now? What are you thinking about? And then after that, we'll chat briefly about ABET.
Oh, fun. That's always a fun conversation. So my foray, or like my entry into engineering education research, came through ASEE, through having experience actually with Andrew Heckler, who's in physics education research at Ohio State. So first kind of just being like, my class was the test tube. And then being like, oh, this is actually really rigorous. It's, the type of, I wonder if my students learned this, but is something we all do as faculty, even if it's just the exams we give. We look at it over time, we're like, oh, they're learning. Okay, this is good. But it really impressed on me the rigor that goes into designing a way of assessing things. When you're actually looking at a specific research question, was my experience with that one. And they were looking at like do sophomore students understand logarithmic axes and graphs? And no. And so how can we design an intervention for that? And it actually helped a lot what they were doing.
And then measure the efficacy of
and then measure the and
Because-
do so in a way that's like, yeah, it's not just me. Like, we can prove this works.
Right.
So I got, as any instructor does, I have a lot of questions. And the question I kind of latched onto was, what is up with these students when I'm trying to teach them programming, which in my case was MATLAB, but even like Crystal Maker, any kind of simulation tools. And Tim and I have talked at length about this. There's just a lot of resistance, and there's a lot of difference between students who are kind of like on board and learning, and those who are very resistant and not really either not learning it or just really don't want to, and what's going on there. And so I kind of want to shorten all of this whole story down a little bit, but so I did a NSF-REEF grant. I partnered with a really great researcher at Ohio State, Rachel Kaifez, and looked at this problem. And like, basically, our students coming in with their own perceptions about modeling? Are they making decisions about what major based on whether or not they feel efficacious about programming? And the answer was no. And, I've got a paper I'm working on for that and everything. But the bigger point of engineering education that I've really come to value is the ways that I can apply that same way of thinking about assessment. It's made me really question my assessments in a way that I did not do even 3 or 4 years ago. Like, it's not just is this testing what I want, but is it going to give me meaningful answer? Is it worth doing an assessment of this? Does the student understand? I've really started to change the way I explain to them, like, this is what I'm trying to understand whether you know how to do. This is what I'm looking for on this assignment. These are the skills that I want you to develop. And so communicating the purpose of the assessments more. I don't know that I'm much more interested in you from conversations like kind of workforce development. Why are students going into certain majors? How can we do things more with working or attracting students to a variety of material science programs and not just 4-year programs at this point. But yeah, I've really enjoyed doing engineering education research, and I've learned a lot about how to be a better instructor from it. So that's been a really valuable, important part of my career.
As a fellow assessment nerd, I very much appreciate what you're saying, but it's completely true when you really get into the mechanics of what different kinds of assessments do and do not measure.
Yeah.
It makes you a lot more strategic in structuring your class to say, of all the things that students are experiencing and learning, which of them do I want to try to measure or at least probe? And which ones can I say, I'm not so much worried about that?
Yeah.
And to then share that with the students, to be fully transparent about it and say, I am giving you this kind of assessment on this topic because I want to understand whether you have whatever it is.
Yeah, and I found that because when I was at Ohio State, of course, I'm teaching these huge classes, and I use multiple choice tests.
Sure.
Absolutely. And they were like bubble because we didn't have every student didn't have an iPad, and we didn't have anyway. And for a long time, I was like, I'm never going to use those again. Like, I really hated using them. But now I've kind of gotten back to having a few of them on there because it's like low-level blooms. That's what we test with those. So.
Right. Yeah. Crafting a good multiple choice
Yes.
question is very hard.
It is.
But when you have a set of good multiple choice questions, it can be very revealing about patterns in your class. And okay, that's a longer topic for another time,
topic.
But I'm there for it.
So sadly, we're running out of time.
Okay. I'm sorry.
Not only because it's not your fault,
Yeah.
it's because Tim and I have a plane to catch.
Yes, of course.
But I didn't want to end without at least touching on the fact that You're now an ABET commissioner.
I am.
Is that right?
Yeah.
So I presume you're in line to eventually be the head of the accreditation committee at TMS.
I am vice chair. So Peo is chair and I'm vice chair. So in a couple of years, yes.
Right. So how have you found that whole ABET experience?
Yeah. So I came kicking and screaming a little bit into ABET, but what I've really enjoyed is the people there. And I have learned a lot from being there. I also really like that there's a lot of, in engineering, like if you have a leadership position, well, just here's your job, get it done and figure it out. Whereas it's really scaffolded. So the way that they educate and build leadership skills is really good. So it's been professionally a really good place for me to learn. And I think I know we've had conversations about the value of ABET or some of its rigidity, I think would be a good word. But I also really, really appreciate that engineers and engineering societies are the ones determining what engineers should be learning. And that I will really support.
Better ABET.
Huh?
It's better ABET than
Yes.
something imposed on us by the government.
Yes.
It's better that we police ourselves.
Yeah.
And, I think, the core values of ABET are very, very sound.
Right.
And it's a very difficult thing they're trying to do, a one-size-fits-all
Yeah.
solution. And, focusing on what's the lowest achievables that
Yeah.
all your graduates are going to accomplish. And I just wish so many faculty wouldn't keep saying, oh, we can't do that because of ABET, because nothing is further from the truth. ABET does not limit anything at all. And they're only asking for a small subset. And ABET's not driving engineering education. Faculty and students and parents and the society should be. ABET's just setting up guardrails.
Yeah. And I think, I've had you as a PEV in my program. We've both done evaluation. And anytime I hear somebody saying like, oh, well, we have to do this because of ABET, I'm like, I encourage you to talk to an ABET PEV, because I can't, as a commissioner, I can't go in and be like, oh, let me look at your thing and that sort of stuff. But or go to the sessions that we hold at the TMS meetings and just ask somebody, do I need to do this? Because most of the time, departments, programs are really making it much harder on themselves than they need to, thinking that they're doing something ABET requires when, we were talking, it's students first. That's still the core of ABET as much as it is of most educators. We're on the same team.
Well, that's great.
Well, before Steve and I skitter off to the airport,
Yes.
the clock is ticking. We always want to have a couple minutes at the end just to offer the guest if there's anything else you want to talk about,
All right.
something you want to brag about. Tell us which Switch 2 game you're most excited for. Whatever might be on the menu, this is your chance to share with the internet.
Darn it. I'm supposed to have something really, really important to talk about. And so I'm going to fail miserably at that. What I will say is I had a really awesome opportunity this summer that if you had asked me 3 years ago, I really didn't think I would. So I got to do a summer fellowship doing research at NAVC Carter Rock. And I really thought that these kinds of positions were only for research faculty. It's you take your disciplinary research on ultrasonics or whatever it is, and you take that around to different labs or different places and say, okay, look, I can do this for you. And I just threw my hat in the ring. And I found out that even if, I don't have any good assessments of was I really helpful to the Navy as a whole? What I did find is that I learned so much about the jobs my students are going to be going into. I learned about, because academia is very different. So there's all of that, just by being a worker in an organization. But also, I found so many places in society at large, but society in ways that are specifically of interest to Navy concerns, where a little bit of teaching experience or a little bit of knowledge about workforce development or how education works, there was a lot of opportunities for like partnerships that I could see. And so I guess I would say anybody who's in a teaching position and you're just like, you really have a lot to offer. Like, oh, well, if you maybe did this, maybe you would attract more high school students. Or did you know this about the way that incentive structures work at universities? Have you thought about doing it this way to get more undergraduate researchers? And yeah, so that's what I would share with the type of people who also listen to this podcast or show up on it, that we have a lot to offer the world, and the world doesn't know it, and they won't until we go out there and show them. That's not just teaching the students, that we have a different way of seeing the world, and it's really valuable.
I think that's a wonderful closing remark. So with that, we'll wrap it up, call it a day.
Get to the
Alison,
airport.
thank you so much
Thank
for
you.
being on the show.
Thank you.
I know after a year and a half of badgering you, we've finally
Well,
made
it wasn't badgering. It was like, I think it was first, I had to miss last year's names, but then it was like last minute at TMS. I was like, oh no, my schedule's spoken for. So yeah, but I'm really excited to be here. This is a great program, and I love being with you guys. It's just like chatting.
Well, thank you.
Thank
All
you.
right, to everyone out there, we'll
Bye.
see you on the next episode of Undercooled.
Thanks.